we want to evaluate and graph polynomials, we need to know what a polynomial is. This is the big ugly definition of a polynomial, but when you look closer, it's really just the sum of a bunch of terms. Each term has two parts to it. First of all, these a's, a1, a2, a3, all the way down to an, or up to an, and all of those are just constants. They're coefficients. They're just numbers. Right? Then you have the x part, x to the n, x to the n minus 1, all the way down to x, and then the last one doesn't have an x in it at all. The thing about that is that that's x to a power. Right? And we start off with the biggest power, x to the fourth maybe. Then the next one would be x to the third, x to the second, x to the first, and the last one would be x to the 0, which is, of course, 1. Notice we don't have any negative powers or any weird things like that. If we wanted to write this as functional notation, we would just put the f of x right in front of it. A couple of terminology things that are associated with polynomials. First of all, the leading coefficient. When this thing is written out in order like this with the x to the biggest power first, the leading coefficient is going to be that coefficient that's associated with the leading term. So the coefficient is the number that's in front of the variable, and the leading term would be the term with the biggest power. That biggest power is called the degree. It's kind of the size of the polynomial. So if we have a bigger power, it would be more terms to it. So its degree is n. Now notice it's n. It's not x to the n. So if you have x to the fifth as your biggest power, as your term with the biggest power, then it's called a fifth degree polynomial, not x to the fifth or anything like that. And then the last one is the constant, and that's this term on the end that doesn't have an x variable in it. We call it constant because it stays the same. No matter what x is, if you're adding 7, you're adding 7. You know, and that's not going to change depending on what x is. So, which of these are polynomial functions? If we look at the first one, look at all the x's. That's how you're really going to tell. We have x to the fourth, x squared, and then the last term doesn't have an x in it at all. This one is a polynomial function because all of those powers are positive whole numbers. So this thing has a leading coefficient. We look for the biggest power, which is the x to the fourth, and the number that's in front of it is just 1. The degree of this polynomial is the biggest power, 4. And then the last thing, the constant term, that's that number without an x in it, just 5. When we look at g of x, look at the x's. We got an x squared, and then this term doesn't have an x in it at all. All those powers are positive, they're whole numbers, so yes, this one's a function too. Which means it has a leading coefficient. The biggest power, the number associated with it, is pi. The degree of this polynomial is the biggest power, which is 2. This is a second degree polynomial. It has a constant term. That's the number without a variable in it, negative square root of 3. For h of x, 5x minus x to the negative 1 plus 7. And it's this x to the negative 1 that makes this not a function because the power, it's a whole number, but it's not positive. Remember, like if we had x to the fourth, we went x to the fourth, x to the third, x to the second, x to the first, x to the 0, and we don't get any negative powers. Lastly, with k to the x, or k of x, we've got x and 2 to the x and a constant term. It's that 2 to the x that makes this not a function, or not a polynomial as well, because the power has to be a positive whole number. It can't be a variable. Now we know how functional notation works. If we have f of x equals 2x to the fourth minus 5x to the third minus x squared minus 4x plus 8, we know how to find f of 3 by what we call direct substitution, because we take that 3 and we directly substitute it for x. So we take all those x's out, plug 3 in, and start solving, or simplifying. So that'll be 2 times 81, minus 5 times 27, minus 9, minus 12, minus 8, which is 162, minus 135, minus 9, minus 12, plus 8. 162 minus 135 is 27. 27 minus 9 is 18. 18 minus 12 is 6, and 6 plus 8 is 14. And there we go. That's direct substitution. It's very straightforward, but it is kind of labor intensive. So I want to show you a new way to substitute called synthetic substitution. Now with synthetic substitution, how we set it up is by just listing the coefficients. So 2, -5, -1, -4, and 8. In order for this to work, our polynomial has to start out where the powers start with the biggest one and work their way down. So notice it's x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and then ending up with a constant term. We finish setting it up by drawing a line like this, and what we're going to do is we're going to substitute 3. All right. This is your first time doing this, so pay attention. What we need to do is first just bring down this 2. Okay? And every time that I work diagonally, I'm going to multiply by 3. So 2 times 3 is 6. Every time we work vertically, we're going to add. -5 plus 6 is 1. So diagonally, 1 times 3 is 3. Then work our way down. -1 plus 3 is 2. Diagonally means multiply. Vertically means add. Diagonally means multiply. And vertically means add. And when you know this number right here, that's going to be f of 3, which is the same number that we found right up here, 14. Let's try it again. Let g of x equal 3x to the 4th plus 2x squared minus 10. Find g of -2. So let's set it up. First of all, we said what was important is that it had to be in order. 3x to the 4th. And notice that we don't have any x to the 3rds. So we have 0x to the 3rds. Plus 2x squared. And no x terms. Minus 10. So list all of those coefficients. 3, 0, 2, 0, -10. We're going to substitute -2. So, bring down the 3. When we go diagonally, we're going to multiply by this -2, so that's -6, and add. Multiply by -2, and add. Multiply by -2, and add. Multiply by -2, and add. That means that g of 2 is going to equal 46. Synthetic substitution is very sweet. Notice how much less work that is. It took up a whole lot less space, and we were able to run through it a lot quicker without needing a calculator or something like that. So if there was like a calculator test or something, it'd be really handy to be able to use synthetic substitution. Let's take a look at the graphs of some polynomials. I've graphed a lot of them here. For the ones in black, y equals x to the 1st. That's a line with a positive slope. Y equals x squared. That's a parabola that opens up. And then the last one is y equals x cubed minus x. We don't want to look at too many particulars here. Really just some general trends that we see. And with all of these curves in black, what we notice is the degree. The degree of the polynomial here is 1, and that ended up being a straight line. When our degree was 2, this thing turned 1 time. When our degree was 3, this thing turned 2 times. So kind of one thing that we notice here is that the degree will tell us how many times our graph is going to turn, how many curves are in it, which we see if it's 1, then there's 0 turns. If the degree is 2, there's 1 term. 3, there's 2 terms. So if there's 7, probably 6 turns. And that works with all of them in the denominator, or in the bottom here too, because we have a degree of 1, 0 terms. Degree of 2, 1 term. Degree of 3, 3 terms. So the number of turns is going to be the degree minus 1. Now, let's take a look at the leading coefficient. What happens if the leading coefficient is positive? That's what happened with all these, all the graphs in black. And as we move from left to right, what we see is that thing going up. So as x gets bigger and bigger and bigger, so does the y value. So for our parabola, we start off going down, but remember that thing turned. And as x gets bigger and bigger and bigger, the y value is going to keep going up as well. And with our third degree polynomial, as x gets bigger and bigger and bigger, this graph is going to continue to work its way up. So if the leading coefficient is positive, then as x approaches infinity, we say, so as x gets bigger and bigger and bigger, f of x, or the y value, also gets bigger and bigger and bigger. Right? But what happens if it's negative? The graphs in blue all have negative leading coefficients. So a slope of negative 1/2. And what happened is this thing went down. The leading coefficient here is negative. We have negative x squared. And this parabola opened down. And even when we have negative x cubed, this thing worked its way down. All right? And that leading coefficient kind of tells us what happens on the right end as x gets bigger and bigger and bigger. When the leading coefficient was positive, as x got bigger and bigger and bigger, the thing went up. Now, with leading coefficients are negative, as x gets bigger and bigger and bigger, the graph will go down to the right. So, if the leading coefficient is negative, then as x approaches infinity, as x gets bigger and bigger and bigger, y is going to approach negative infinity. Notice, positive, positive infinity. Negative, negative infinity. So, the leading coefficient tells us what happens on the right end of the graph. So, that's all we need to know to get a very general idea of what is the most likely shape of f of x. When it's 3x to the fourth minus 2x squared minus 3, a very general idea, without getting too specific, is going to be that as x gets bigger and bigger and bigger, the leading coefficient here is positive. That means that our graph is going to go up to the right. Since the degree is 4, that means it's going to have 3 turns in it at the most. 1, 2, 3. So this is the most likely shape of this graph. For g of x, negative 3x to the third plus x minus 9, since the leading coefficient is negative, negative 3, that means the right side of the graph is going to go down. Since the degree here is also 3, that means it's going to have 2 turns. So working backwards, there's 1 turn, 2 turns. And that would be the most likely shape of a third degree polynomial.